Good afternoon, students. In this video I am going to explain about some of the important axioms of the probability. In the last class we have discussed about the probability. We have solved some of the problems in the probability based on the concept permutations and combinations. And from this present topic we can expect one long answer question. Based on these axioms we are going to solve some of the problems. One long answer question can be expected in the exam from the topic, that is axioms of probability. That is nothing but conditions of probability. Axioms nothing but these are the statements or the conditions for the possible probabilities. And coming to the first axiom, there are three axioms in the probability. First axiom is nothing but if we have a sample space in which if we calculate, if we have a sample space is nothing but total number of possible program outcomes of an event is called sample space. Total number of possible outcomes of an event is called the sample space. We are having some set of events that is called sample space. If we calculate the probability of any event on that set, any event in that set must have the value, it must lie between 0 and 1 only. It should not be negative, it should not be more than 1. That means what? Whatever you are going to calculate the probability of an event from a given sample space, it must be between the 0 and 1 only. That means what? The probability of any event, the probability of any event should lie between 0 and 1. That means what? 0 less than or equals to probability of an event less than or equals to 1. That means what? That requires to have the probability of any event must lie between 0 and 1. The probability of any event may vary from 0 and 1. The within 0 and 1 only we must get the probability of any event in the given sample space. It should not be a negative number, it should not be a more than 1. First axiom of the probability. First axiom of the probability. Probability of A is nothing but it is an event which is defined in a sample space. Sample space is nothing but total number of possible outcomes of an experiment. This is probability of A must lie between 0 and 1. For A is nothing but it is an event. A must be subset of a sample space. This is valid statement. That means what? We are having a sample statement, we are having a sample space in which we are having some events. The probability of that event is given this statement. That event must be a subset of the given sample space. Sample space is nothing but the total number of possible outcomes. Here from the total number of possible outcomes we are taking one possible outcome, so that this one possible outcome must be a subset to the total number of possible outcomes. First axiom, probability of any event, that event is a subset to the sample space, it must lie between 0 and 1. It should not be a negative number, it should not be more than 1 value. And coming to the probability of sample space 1 only. That means what? Sample space is nothing but total number of possible outcomes of an event. Obviously the total number of possible outcomes will be 1 only. If we go with the possible outcomes of any experiment, you can have the probability of that possible outcomes of that event is that sample space is equals to 1 only. And this is the second axiom in the probability, that is probability of sample space. Probability of having the total number of possible outcomes of an experiment is 1 only always. And coming to the third one, if A and B are mutually exclusive events, that means we are having a sample space that is S in which A and B are mutually exclusive. These mutually exclusive is nothing but the probability of A is mutual exclusive to the probability of B, so that these two are called as the mutual exclusive event. So that in a sample space we are choosing A and B which are mutually exclusive events, then it has to satisfy the condition, that is probability of A union B. This is here A is an event, B is also here event, so that we are going with the A union B, that is A event union B event, and then we are calculating the probability of A union B, which must be equals to probability of A plus probability of B. These three are very important axioms in solving the problems, and from this topic we can expect one long answer question. If you are good at these three axioms, you can able to solve the problem based on these axioms of probability. Then I am going with some basic examples based on these axioms of probability. That means what? I am going with one particular experiment. In that experiment, I am going to verify all these three axioms of the probability. I am going with the one experiment. In that experiment, I am going to verify these three axioms. Then I am going to see so first example, we are going to verify the axioms of the probability. The first example I am taking tossing a coin. Tossing a coin. In this example, we must verify these three axioms of the probability. First one, the probability of any event must lie between 0 and 1, and the probability of sample space is equals to 1. The probability of A union B, where A and B are the mutual exclusive events, then which must be equals to probability of A plus probability of B. Then I am going with the tossing of A. First you must, whenever you see the question, first you must understand what is the sample space. Sample space is also named as total number of exhaustive cases. That means what? The sample space is nothing but the total number of possible outcomes of an experiment. If you toss a coin, then there is a possibility of two things, either head or tail. So that sample space we can have the either head or tail. These two combinedly named as total number of possible program outcomes are named as sample space. Sample space is denoted with capital S. It is a set and which is having the head and tail, and rather than S and H and head and tail, we cannot find another programmable outcome. So the total number of programmable possible outcomes in an experiment is named as sample space. Sample space is a set which is having head and tail. In this we are going to calculate the probability of H. First I am going to calculate the probability of each event. H is an event, T is also event. By calculating the probability of H, I must get the probability value must lie between the 0 and 1. By calculating the probability of tail, I must get the value in between the 0 and 1. Then only it satisfies the first axiom of the probability. So that probability of head, the formula of the probability, we know that number of favorable cases by the total number of exhaustive cases are the total events are there in the sample space. So that here the number of probability of getting head is 1, and out of sample space there are 2, so that it is 1 by 2. 1 by 2 is satisfying the first condition, so that it is satisfying the first condition. Then I am verifying with the tail also, probability of getting the tail. The formula for the probability we have studied, that is the number of favorable cases by the total number of the possible outcomes, that is nothing but events in the sample space. So that probability of getting tail, only one chance we can have, so that 1 and the total number of samples are total number of sample space, total events in the sample space is 2, so that probability of getting the head is 1 by 2, probability of getting the tail is also 1 by 2, and probability of getting the all the events must be less than 1 only. Individually this is probability of getting head is 1 by 2, which is satisfying the condition 1. Probability of getting the tail is also 1 by 2, which is also satisfying the condition 1. And coming to the second condition, probability of sample space. Sample space is nothing but what? The total number of possible outcomes. The total number of possible outcomes of an event. Total number of possible outcomes of an experiment. If we perform one experiment, the total number of possible outcomes, that is called, it is a sample space. So that probability of sample space, the total number of program outcomes will be, and this head tail only, and so that we can get only one time, so that here the probability of getting this one is 1 only. Probability of getting the total sample space is 1 only, that is probability of S is equals to 1. Or we can go with this one, probability of H is nothing but probability of S is nothing but probability of all the events. Probability of S is nothing but the summation of probability of all the events. You can go with this formula is probability of S is equals to probability of head, and the probability of tail, that must be is equals to 1, so that it is 1 by 2, and here also plus 1 by 2, which is equals to 1. That means what? The probability of sample space, the probability of sample space is 1. First condition is satisfied and the second condition is satisfied. First condition is what? The probability of any event from the probability of any event from the sample space must lie between the 0 and 1. It should not be a negative number, it should not be a more than 1 value, and that event must be subset to that is sample space. The first one. Second one is that is the probability of sample space must be equals to 1. That is nothing but the probability of sample space is equals to summation of probability of all the events which are there in the sample set, and that must be equals to 1. And here the probability of H is 1 by 2, the probability of tail is also 1 by 2, both are remain same, so that these two events are named as mutually exclusive event. These two events are named as mutual exclusive event, and so that we are going with the last case, that is the probability of A union B is equals to probability of A plus probability of B. And here probability of H union T is equals to the probability of, here first I am going with the probability of H union T, and I am simplifying this one. H union T is nothing but HT only, because the total number here we are going with set H union set T is nothing but H comma T only. Then the probability of H and T, H and T is nothing but sample space only. The probability of HT is nothing but S only there, so that probability of S is equals to probability of H and plus probability of T, and in such a way we can verify all the three axioms in the given example. That example here, tossing a coin. I am going with the another example in verifying the axioms of the probability. Axioms of the probabilities is very, very important in the examination point of view. Not only in the examination point of view, to solve the problems of the probability, mostly we will depend on the axioms of the probability. Second example I am going with the explanation, that is in throwing a die. In throwing a die, we are going to see this one. In throwing a die, then we must verify all the three axioms of the probability. First we must know what is die. Die is a cube, actually it is a cube which is having the 6 faces. Each face is assigned with one particular symbol, that is dots, and that dot, by counting the dots we can give the numbers. This is 1, 2, it is having the 6 phases, means 6 numbers we can assign, so that the total sample space is what? It is having 1, 2, 3, 4, 5, 6. It is having the 6 phases. so that each phase is assigned with one number 1, 2, 3, 4, 5, 6, so that the total sample space, the total number of possible outcomes, if I throw a die, then what is the probability of getting a phase? That may be 1, that may be 2, that may be 4, 5, 6. More than 6 we cannot get, because it is composed with the 6 phases only. So that from these 6 any one we can get, and so that the total number of possible outcomes, that is nothing but number of exhaustive cases, that is about 6, and the sample space is nothing but it is a set which is consisting of all the possible outcomes. Then first one is completed. Then I am going to verify this one. First I should verify the probability of each event, the probability of each event in the sample space. Probability of 1 is nothing but we can have 1 only, number of favorable cases are 1, and the total number of exhaustive cases are 6. Probability of 2 is what? We can have the only 2 is 1, 2 is there, so the total number of possible outcomes are 6, and now P of 3, probability of 3 is equals to, this is also 1 by 6, and here also 1 by 6. Probability of 4 is also 1 by 6. Probability of 5 is also 1 by 6. Probability of 6 is also 1 by 6. So that the probability of 1 is 1 by 6. Probability of 2 is also 1 by 6. Up to probability of 6 is also 1 by 2. If you go with the statement, that is nothing but what it is? The probability must lie. Probability of any event, that events are 1, 2, 3, 4, 5, 6. Probability of A is between 0 and 1. Probability of 2 is also between 0 and 1. Probability 3 is also between 0 and 1, so that it is satisfied the first condition. The probability of 1 is 1 by 6. Probability of 2 is also 1 by 6. Probability of 3 is also 1 by 6. Probability of 4 is also 1 by 6. The probability 5 and probability 6 also 1 by 6. All these lies between 0 and 1, and it is not in a negative number, it is not exceeded after 1 also, so that this is satisfying the condition. And all the events 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, all these are subset to the sample space. Sample space is a set which is having the 1, 2, 3, 4, 5, 6. Then these events are subset to the sample space. Coming to the total, the probability of sample space. Sample space is nothing but the total number of possible outcomes. Possible outcomes are 6, and the total number of possible outcomes we can achieve only one time, so that the probability of yes is equals to 1. And here probability of 1, probability of 2, up to probability of 6, all are having the same number that in the probability, so that all these events are named as mutually exclusive event, as we said earlier in the first example. And these all events also mutually exclusive events. And coming to the third point, we have to verify. From this we can directly you can write probability of H union T is equals to probability of H plus probability of T. But here we can directly go with probability of S is equals to probability of 1 plus probability of 2 plus probability of 3, like that up to probability of 6 we can go. And here we can have, this is 1 by 6 plus 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 1 by 6, which is equals to 6 by 6 is equals to 1. That means what? The probability of sample space, the probability of sample space is equals to 1. The probability of sample space always calculated. The probability of sample space always calculated. Probability of union of all the events in the sample space, that is nothing but probability of all, the probability of union of probability of union of all the events in the sample space is nothing but it is a probability of sample space. Like this we can verify the 3 axioms of the probability. And coming to the third example, we are going to verify all the 3 axioms of the probability in this example also. Then we are going with, yes, in this we are going to see the one more example, that is in tossing two coins, we are tossing the two coins at a time, whereas here in the first example we have verified all the axioms of probability by tossing only one coin, and here we are going to see the probability, we are going to verify the axioms of the probability by tossing two coins, that means what? I am having the two coins, this is one coin, this is another coin. If I toss the two coins, then in one I can have the head and head, I can have the head and tail, I can have the tail and head, I can have the head, tail and tail. The total number of the exhaustive cases are 4. Total number of exhaustive cases are 4. All these cases, all these program outcomes are there in the set. That set is named as sample space. Sample space is a set. Sample space is a set in which we can have all the possible outcomes, all the possible events of an experiment, that is denoted with S. S is equals to H, head tail, tail head and tail tail. So that we are going to verify the first axiom of the probability. That means what? The probability of any event, must lie between the 0 and 1. The probability of any event must lie between the 0 and 1. That means what? The probability of H and H must have in between 0 and 1. The probability of H and T must have between 0 and 1. Probability of T and H must be in between 0 and 1, and the probability of TT also must be in 0 and 1. So that we have to verify this one. The probability of head and head, the probability of head and head, we know the probability formula, that is number of favorable cases by the total number of exhaustive cases. That means what? Number of favorable cases, head and head we can have only one, head and head we can have only one, and the total number of exhaustive cases are 4. And coming to here, we can go with this is combinedly head tail, tail head, so that, and by having one head and one tail, by having the one head and one tail, and what is the possibility of getting the one head and one tail, and combinedly we can go with this one, probability of head and tail. Probability of head and tail, we can have the two number of favorable cases out of 4. This is 2 by 4 and this is 1 by 4. And coming to the next one is probability of tail and tail. Probability of tail and tail, only one favorable case we are having out of 4 number of exhaustive cases. 1 by 4 it is less than 1. 1 by 4 it is less than 1. And 2 by 4 is nothing but it is 1 by 2, it is also less than 1. Probability of TT, that is equals to 1 by 4, which is also less than 1. It is satisfied the first axiom of the probability. Probability of any event in the sample space, probability of any event in the sample space must lie between the 0 and 1. So that here probability of this event 1 by 4, it lies between 0 and 1. Probability of H and T, and it lies 0 and 1, and the probability of TT, it must lie between 0 and 1. And we know that is probability of sample space. We know that the probability of sample space is what? The probability of having all the outcomes. Probability of having all the outcomes, that is 1 only. So that the probability of sample space is 1 only. In another manner, you can define this one also. Here we can go with the probability of the third one. I am going with the probability of HH union, then HT union, then TT. So that you can go with this one is the probability of HH plus probability of HT plus probability of TT, and this is equals to 1 by 4 plus 1 by 4 plus 1 by 2. This is 1 by 2 and this is 1 by 4. If you simplify this one, the probability of total sample space is equals to, you can get this one is 1. The probability of sample space is nothing but the probability of union of all the events, probability of union of all the events, which is equals to 1, that is nothing but summation of individual probability of all the events which must be equals to 1, and these are very important 3 axioms in the probability. I am revising all the 3, and before going to conclude this session, first one is, if you calculate the probability of any event which is defined in a sample space, that must lie between 0 and 1. Coming to the second one, probability of sample space, probability of getting all the possible outcomes is always 1 only. And the third one is nothing but, if A and B are, that means A and B are the events in the sample space. If A and B are mutually exclusive events, then probability of A union B is equals to, probability of A union B is equals to probability of A plus probability of B, and this probability of A union B is nothing but it is probability of S only, that is probability of sample space. Likewise, you can verify the probability of any given experiment. Likewise, you can calculate the possibility of existence of the probability of the given question, when that probability is permissible or not. By verifying these 3 statements, you can easily tell that that is permissible or not permissible if the given question is. In tomorrow's class, in the coming class, we are going to solve the problems, and we are going to prove some of the theorems in the case of probability based on 3 axioms, which are very important in the examination point of view and as well as in solving the problems. Thank you.